However, in the absence of wind speed, the adjusted R square reached a maximum, indicating that wind speed does not improve the accuracy of the TA model. To sum up, it is sufficient to use remote sensing data elevation and Julia days as independent variables for the model. To understand the universality of the built model, the multilinear regression model was verified using the 2018 to 2019 dataset. The random forest algorithm was verified using the reserved test dataset. And analyzing the daily average TA and errors estimated by multiple linear regression from 2018 to 2019, it was found that the temperature and errors on the time scale and distribution characteristic and the spatial distribution map of RMSE shows that the model in mountainous and plateau areas generally performs worse than in plain areas. Because the data of two adjacent clumps of less satellites of different periods, remote sensing images of the entire study area cannot be obtained on the same day, so the basin can only be divided into two parts for compression. Chosen 4 images with fewer clones, then calculated the difference between the spatial interpolation result and the regression model estimate. The error of TA distribution obtained by inverse distance weighted in the area is related to the underlying surface. At this point, we have calculated the optimization of the near surface air temperature data in this area. TA is very important for the calculation of actual evapotranspiration. Therefore, we are bringing the two methods for calculating TA into the remote sensing evapotranspiration model and analyze the changes in flux and ETA accuracy. This is the process of calculating ETA. And we confirm the location of flux data and the distribution of different years of each treatment. The two irrigation methods are border irrigation under plastic mulch, that's BM, and drip irrigation under plastic mulch. This is DM, and the data collection is supported by the National Field Scientific Observation and Research Station on efficient water use of oasis agriculture in Wu of Gansu province. The TA calculated by the regression model and the interpolated meteorological data was substituted into the RN calculation formula and then verified with the flux data from 2014 to 2015. The results show that the improvement of TA precision can effectively improve the calculation result of RN. For the energy balance model that calculate evapotranspiration, the difficulty of sensible heat flux lies in the calculation of the latent heat flux lines in the calculation of sensible heat flux, which directly determines the result of latent heat flux. One of the innovation of the metric model is its selection conditions of dry and wet points, and it is combined with reference evapotranspiration value to determine the assumed value of H and LE as the two extreme value points. The condition for selecting wet and dry points can continue the previous study. The point with NDV less than 0.05 and higher temperature were identified as dry points. Surface albedo was between 0.18 to 0.25 and NDV greater than 0.7, and lower temperature points were considered as wet points. Aerodynamic resistance is another important parameter when estimating sensible heat flux, which is easily affected by the buoyancy because the cold and hot air. To solve this problem, an iterative algorithm was used to calculate the aerodynamic resistance and sensible heat flux to reduce the effect of buoyancy. When first estimating aerodynamic resistance, the atmosphere is assumed to be in neutral stability. Starting from the second iteration, considering the stable state of a near-surface atmosphere, a parameter for judging atmospheric stability, that is the morning observable length, is introduced. When the coefficient A and B in the linear relationship between vertical air temperature gradient and surface temperature, aerodynamic resistance, fraction, wind speed, and sensible heat flux remain unchanged. The iterative cycle algorithm is terminated. Many studies have found that the algorithm terminates after a 4 to 7 iteration cycle. Using the flux observation data to verify the inversion of G, H, and LE in 2014 to 2015. With the use of the model, the consistency of verification result is high. Extracting the available satellite traced daily water consumption data and comparing with the calculated value of the metric model, the R-square of 2014 to 2018 is between 0.44 to 0.98. The overall R-square of DM treatment is higher than that of BM. Although 90% of flux contribution source area are distributed within 150 meters of the mirroring point, which is greater than the resolution of Landsat 8. The flux value and ETA in a small range are still be verified intensively. Therefore, it needs to be corroborated with other datasets within the region. Comparing the 8-day water consumption obtained by two products, it is found that the value calculated by Landsat 8 is generally higher than that of modest product. The ETA value obtained by Landsat 8 and metric model was used to extend the growth period scale. The water consumption of maize at each growth stage under the two irrigation methods from 2014 to 2015 was obtained and compared with the observed value of water balance, BREP and EC. There was a difference in the daily water consumption between the two irrigation methods, but the difference was often small, and the results observed by BREP and EC were not always the same. Comparing the calculated and observed value of differences, it is found that most of differences are in the same direction as EC, except for some cases where the indifferences between the calculated and observed are inconsistent. So summarizing all the above work, it is found that using non-meteorological data to establish a regression model for near-surface air temperature is feasible for areas with sparse meteorological station. Comparing the regression model and the interpolation result, it is found that the interpolation method has a large error in temperature estimation for desert and mountains. The improvement of the accuracy of temperature dataset has improved effect on the estimation of net surface radiation. For 2014 to 2018, the single-day estimation accuracy of metric model for water consumption during the mass growth period was 0.44 to 0.98, and the analysis and calculation results show that the ETA difference caused by the two irrigation methods can be obtained by inversion, and the direction of difference is in good agreement with EC observation results. This part of work provides effective support for satellite remote sensing to obtain farmland differences and lays a solid foundation for the research. That's all. Thank you, guys.
Samuel, your
okay.
phone not open.
Okay, now, okay. Thank you very much, Louis, for your nice presentation. Very nice work. A lot of work anyway.
Thank you.
So that we have a couple minutes for some questions. There are some questions. Anyway, you know, we will in the future we will have the emails, so a student also they can talk each other about some specific topics. Okay. Our next speaker is, the title is Satellite Monitoring of Crop Coefficient and Water Requirements of European Hazelnut under Mediterranean Semi-Arid Climate Conditions. This presenter, the speaker is Daniel de la Fuente from our lab. Daniel?
Yes, good morning to everyone and good evening to everyone. Let me share. Okay, you can see it?
Yeah. Okay, thank you.
Okay, well, my name, as said, Professor Ortega is Daniel de la Fuente. I'm a Ph.D. student right now in my 4th year of the Ph.D. And my work is about satellite monitoring of crop coefficient in water requirements of European hazelnut in Chile under Mediterranean semi-arid climate condition. My supervisor is the PhD Samuel Ortega. And in order to contextualize you, Chile is now in a mega drought. Is entering, it is 12 years, the current drought. Chile is rightfully named this way, a mega drought. It's starting in 2010. It is the longest drought in Chile and has been over the last millennium with a mean rainfall deficit about 20 and 40%. And by this problem, many farmers have been forced to move to the south part of the Chile and relocate these cultivars and different crops in order to search a new irrigation areas. And also, as a background, and some interesting hazelnut factors in Chile, we have this problem, a mega draw for one part versus an economic expansion of this crop. This crop is increased in planted surface in the last decade by about 500%, and 87 increase between only 1 year, with expansion to the southern part of the Chile. The Maule region, when we are here in the University of Utalca, has half of the national planted area of hazelnut, and has also the world's largest hazelnut orchard. And the problem right now with all of that is we have a problem with the crop monitoring, also in large areas, different crop coefficients for different trellis system or different texture of the soil, and also unknown what is the real crop water consumption requirements in Chile, because the hazelnut, the European hazelnut, is originally from Italy or Turkey under rain-fed conditions. So the challenge in the Chilean European production of hazelnut is to have a sustainable and ensure yield and quality with an efficient water use. Why? Because for the 2023 triple kind of currently cultivated area, a large territorial expansion to the south, the actual mega draw. And so what happened with the physiological stages of the crop? The crop is of the different area, and what happened with the Mediterranean climate, and this challenge is directly related to supplying the crop water demand and quality and opportunity in a sustainable way, considering also the crop is sensitive to water stress under different climate conditions. So the main objective of my doctoral thesis is to determine the crop water consumption under the seasonal crop coefficient of the hazelnut for a sustainable water management using an energy balance model. Okay, that is using a satellite monitoring. That is some of the advantages, as stated in another presentation: the continuity of data, optimization of agricultural management, usefulness in extensive areas, and so on. But the main two sources of satellite images is the European way and the American way. And we have a lot of researches using this source, the USGS, with a Landsat satellites, because has a thermal band. And the literature and different researches shows that the metric model is one of the best performing model to map the evapotranspiration in different resolution. The advantages from the metric model is based in the surface energy balance method and has a model auto-calibration called CIMEC. Also, we have an acceptable or errors in the spatial and temporal variability of 5 to 20%. And when we apply the metric model under full cover crops, such as a big leaf effect, it's not necessary to know what is the crop. However, the application under fruit crops with sparse canopies, such as vines or olives, is very recent. And also we have some adjustment in some critical algorithms of the metric model, such as the leaf area index or soil heat flux or COM, the length room. So what happens in the European hazelnut orchard? We have a mixed canopy with a soil, with shadows, the canopy again, and so on. it's not as easy as just getting data. We need to model in the crop and model and correct the different algorithms of the metric model. And our background in the Citra is about 7 papers and researches that we use different calibration of the metric model from 2012 to last year in different crops. So for my doctoral thesis, my experimental site is located in the Central Valley of Chile, in the Maule region, and the largest hazelnut orchard, as said later. In this point, in the Camarico zone, the more important data here is prevailing wind direction for calculating the footprint of the ecovariance. And we have measurement during 3 growing seasons, and also the data I will show you is preliminary data because the project is going on. We installed an ecovariance tower over 6.5 meters above the canopy, 1 meter above the canopy, and 6 from soil. We installed net radiometers, sonic anemometers, infrared gas analyzers, also a thermocouple here, as you can see. The orchards, or the branch of the hazelnut has a multi-axis trellis system with 8 to 12 branches per branch, and also the diameter per branch is 3 to 7 centimeters. So you can see this is the orchard, this is the ecovariance tower, and the location of the measurements during the 3 growing seasons, and the estimation of the footprint here with a fetch with an average of 150 meters. Also, we monitoring during the seasons the NDVI values. In green, you can see the 2021 season, and purple, the 2017 and 2020 growing seasons. And also we monitoring during the whole season the midday steam weather potential, the fractional cover, phenological stages, and so on. And to compute the metric model, in collaboration with Samuel Ortega Salazar from the University of Nebraska, we use the EE-FLAX metric model as a big data computation modeling to estimate the crop water consumption and crop coefficient. So this is the first results. Here you can see the energy balance closure from the ecovariance for 2 growing season in 30 minutes time interval. The incoming energy and the outgoing energy here with an R square 0.97, and for the another season also 9.7, and a slope in 86 and 0.91. Is a good relationship when compared with the literature. That is good results from the result also for a hazelnut orchard that we have. Also the energy balance, but daily time interval values also applying the Bowen rate to closure, and the values of also very good for our growing seasons, 0.9 in the slope and 0.98 for the 2 growing seasons. And this is the hazelnut energy balance measurement during the whole season. In green for the 2 graph, you can see the net radiation. In blue, the blue line is the latent heat flux. And red is the sensible heat flux, and you can see here this soil heat flux. The more important data here is and interesting is in the first season, you can see a summer heat wave that changed the values of the latent heat flux to the down and inverted with the sensible heat flux. That is caused by the plants has water stress, and also reflected in the steam water potential of the plants. And for the second season, in February, we have a summer precipitation, and also the energy balance change during almost 2 weeks, also changing the water requirements of the plants. The same as showing in the last slide is showing here in red. The red values is the reference evapotranspiration from the meteorological water station, and in red you can see the crop water consumption from our AD covariance stations. And here you can see the same. When we have in the second season the precipitation events, also the reference and crop evapotranspiration is going down, and final in the a summary of the different seasons, we can compute real values of crop water consumption in cubic meters. Is with an average of 800 and 500,000. And also we compute the water use efficiency for now the 2 growing seasons, comparing with the water consumption and yield. Then, as an example, you can see the evolution of crop coefficient during the growing season, and in red is the FAO 56 KC values tabulated in the book, and in the black line you can see the real KC values from our AD covariance, and here validated from 2 growing season is the summary of the KC values locally, KC values from the hazelnut orchard, during the whole season. Of course, there's a lot of difference between the KC from literature, so against the AD covariance. And the blue lines are the steam water potential for the season. So when we analyze different plots in the orchard, in the largest orchard, we analyze 2 sectors, 39 and 62. And the first sector is the most vigorous and oldest from this field in a different architecture. And now, and this is possible to analyze with the metric model in values, but also seeing this map at pixel scale. And the second plot is a young orchard with a low fractional cover. When we analyze the spatial and temporal evolution of the water consumption, we see this variation in crop evapotranspiration against 2 different systems, irrigation systems in the field. And also we can compute for each plot of the field satellite-based KC values calibrated also by the metric model, and see with SIG maps what is the evolution of the KC in the different plots of the orchard. Considering these cases, because for example, when we have the precipitation in February, the soil doesn't have weeds, and 2 weeks later have weeds. Weeds is reflected in the satellite images and also in the KC values of the Edico-Vargas. So what is the next steps? In the next steps for us and for the team is to use surface renewal technique to validate the metric model in different planting densities, varieties, and locations in the southern Chile. In zones that we have different planting frames, plant vigor, heights, fractional cover, and so on. And also the projects starts in 2016 and continue to 2024, financed by Ferrero Company, and to acknowledgement to the Citra teams, so to the Citra team, to my pre-grad and postgraduate students, and all the team from Citra and the international associate researchers of the Citra team. Thank you very much.
Okay, thank you, Daniel, for your presentation. Okay, our next speaker, or next presentation is spatial-temporal pattern and dynamics optimization of crop water and nitrogen in the arid area of northwest of China. The speaker is PhD student Junfei Fan. Junfei, you have now, you can put your presentation, please. Thank you.
Okay. Can you hear my voice?
Yes, yes, it's fine.
Okay, okay. Good morning and good evening, professors and students. It's an honor to participate in this PhD workshop. My name is Yunfei Fan, and my supervisor is Professor Su Fen Wang. The topic I report today has a little change. Spatial temporal pattern and dynamic optimization of crop water consumption in the arid area of northwest China. Okay, now for my report. I will start with the following 5. First, the background. As we can see from the left, China's agricultural water use has been declining in recent years. Of course, including water-saving factors, but more importantly, a reduction in total available water resources. And there is still a big gap in irrigation water use coefficient between China and the developed countries. The right shows climate change and continued population growth in the future will cause a crisis in water and land resources, which will put crop production under pressure. There are 2 methods for optimizing the crop water consumption. One is the traditional mathematical method. This method considers factors such as vapor transpiration, effective precipitation, water price reform, water shortage, climate and policy changes. And the specific methods include fuzzy variables, stochastic optimization, nonlinear dynamic programming, 2-stage optimization, and many algorithms. The parameters of such methods are subjective and difficult to verify. While intelligent optimization algorithms are very effective in solving complex problems, the other method is spatially distributed optimization model, which is composed of spatial data, reflecting the spatial variability of crop growth and influencing factors, and can achieve fine optimization of spatial grids, but less optimization considering both temporal and spatial dimensions. Based on the above problems, we established such a research framework. We established a distributed crop water consumption model using meteorological, topographic, soil, and other data. And we selected 22 indicators to analyze crop suitability. Planting structures were extracted using remote sensing data. Then we combined the cellular automata model and the Jensen model to realize the spatial temporal dynamic optimization of crop water consumption by establishing an optimization model and constraints. Finally, we can get crop spatial distribution, crop water consumption at each growth stage in space. And this is a C-Jensen model we established. Here, each cell is a spatial grid. First, we build the Jensen model on each grid and optimize it spatially using the transformation rules of cellular automata. In the optimization model, we use the net irrigation benefit to represent the economic benefit, the water productivity to represent the social benefit, and the ecological service value of each grid to represent the ecological benefit. This is a model-specific process. We first judge whether a grid is a cultivated land, because here we believe that all crops should be planted on cultivated land and should not encroach on other land types. Second, we judge which crops are more suitable for the grid based on the crop suitability. After simulating crop distribution spatially using CA model, we developed an adaptive cellular genetic algorithm. This algorithm is used to optimize crop water consumption on time scale. As can be seen from the figure on the right, the main feature of this ACGA is it needs to perform crossover and mutation operations in the cell space, and the crossover and the mutation probability changed adaptively. That is, in the early stage of algorithm search, the ACGA convergence speed is accelerated and the local search ability is enhanced in the later stage. This algorithm is similar to the general genetic algorithm. The difference is that all its crossover, mutation, and replace occurs in a 3x3 cell neighborhood, so that the solution set can be smoothly distributed in the entire population. The constraints are enforced for each search. The iterative search of the model is random, avoiding subjectivity. The crop water distribution in each growth stage is determined by the water sensitive index in the Jensen model. We applied the CA Jensen model to the middle reaches of the Heihe River Basin in the arid area of northwest China. The Heihe River Basin is the second largest inland river basin in China. The middle reaches of the Heihe River concentrate 90% of the arable land and the population in the whole basin. The below are some precipitation and evaporation data for the study area. The mean annual temperature is 3 to 7 degrees Celsius. The mean annual precipitation is 15 to 150 millimeters. The potential evaporation transpiration is about 1,410 millimeters. This is the optimization results based on the CWRCE model. For base year 2015, net irrigation benefits increased 0.2 yuan per cubic meter. Crop water productivity increased 0.559 kilogram per cubic meter, and the total water consumption decreased 57 million cubic meter. The target year 2030, due to the limitation of the cultivated land and the reduction of available agricultural water, the optimization results of net irrigation benefits and the crop water productivity in 2030 are still better than 2050. The comparison shows that the adoption of the optimization scheme can make the agricultural development in the middle reaches of He River show a gradually improving trend in the future. This is a spatial comparison result. Maize still tends to be intensive. Wheat and cash crops tend to be decentralized. The scale of maize should not be expanded, while wheat and cash crops should be increased appropriately. The adjustment of planting structure is an important reason for the good development of agriculture. This is the results of optimization on time scale. According to field research and yearbook data, the actual irrigated area in 2050 accounted for 85% of the cultivated land area. Each irrigation area has supporting irrigation engineering facilities, and the actual irrigated area after optimization can reach 95%. The crop water consumption at each growth stage has been compared and verified, which is very close to existing research. Our conclusion is the constructed model can increase the net benefit of unit water and improve crop water productivity. Second, the model comprehensively considers the social, economic, and ecological benefits of the region and can make different planting and irrigation decisions according to development needs. The third is it provides a new method of optimizing the temporal and spatial pattern of crop water consumption. Okay, that's all. Thank you. Thanks for your watching.
Okay, thank you very much, Yunfei, for your nice presentation. Okay, the next speaker, or the next topic is crop coefficient dynamics in commercial vineyards measured by surface renewal technique, industrial challenge for accurate modeling. The speaker is the PhD student, Sebastían Vargas. Sebastían.
Hi to everyone. Well, thanks a lot, Samuel, and the people from the China Agricultural University. And I would try to be very brief here. This is one of my topics on my PhD. So the idea here basically is to being able to use this technique, which is as a lower cost and as more easy to operate in industrial scale, to even how accurate we can build KC curves. And if you're able to actually exploit that information to assess water demand and to finally have a protocols of irrigation. The problem is well known. We have an historical drought. Rain is getting lower and lower, and same happens with our reservoirs. The reservoirs, I'm not showing that information here, but the reservoirs in Chile, most of them are really low, as well as the other problem is with increase with global climate change. It's not just that we have less water, we are seeing an increase on the demand as well, measured as ET. So we're projecting higher evapotranspiration demand from the environment. So less water, we're getting less water, and we need to use even more, also for the pressure of growing more food and so on. That's what I'm showing here, how the ET is expected to be in the future way higher. So the problems I'm trying to assess in my PhD is basically that obviously viticulture must adapt to this new scenario through new technologies, okay, for accurate irrigation management and to optimize the water use. So we need basically accurate and low cost, easy to operate and commercially scalable technology to assess the crop demand, okay? In our case, based on an accurate KC determination. And the other, it's a reduced amount of water by using tools like RDI, regulated deficit irrigation, that might, even though we know a lot and we have a considerable amount of information, several traits on the impact on grapes have no conclusive findings. So we need more research on that. So those are my two main topics. I will articulate today in the use of the commercial use of surface renewal as a tool to assess demand of water. So there is several ways to, all of here, I guess we know, there's several ways to assess evapotranspiration. Most of them are quite complicated and costly to assess. So we have eddy covariance, Bowen ratio, optical scintillation, costly and a little bit difficult to operate. And other ones are a little bit more unpractical, like lysimeters. So surface renewal is a technique that is way less costly and it has a pretty good performance. So, but needs some things to be fixed. So needs for calibrations and commercial scaling testing. Sorry. Basically, how is that costly? Because it's way more simple than eddy covariance. So we're using the residual of the latent heat flux. So we measure net radiation. We're measuring sensitivity heat flux and soil heat flux. The way we measure sensitivity heat flux is way different than eddy covariance. I will talk a little bit of that, but it's a simplified version. So we don't have to have an RGAS to assess LE. The way it operates, it's based on the fact that if we measure temperature in high frequency, we will see these ramp-like coherent structures, okay? So these structures are, let's say, theoretically, they are characterized as parcels of air that get in contact with our canopy. Then they increase their temperature, they get unstable, and they get replaced. They go away and they get replaced by a new parcel of air. So if we measure in high frequency the temperature, we can basically characterize these ramp-like, and by the amplitude of these ramps, we can obtain heat flux. Okay, so sensitive heat flux. That's the way we do it. So basically, the objective is to measure an ET by this technique and see how accurate it is against EC and against eddy covariance. And if we can build KC models that are more accurate over the time, and these quite different scales, scales of time, scales of phenology, and temperature-based scales. So what we have a big plot where we are measuring soil moisture, stored conductance, stem water potential. We have a surface renewal station. We have an eddy covariance station as well. This station also is a eddy covariance, but also, as I told you, it's not a complete one. We can measure LE. We also do it by eddy covariance, but as a residual. This it's the experimental plot, which is located in Maule Valley, is around 6 hectares of land that we control, where not only we have these energy balance stations. So here's the surface renewal station, and here I'm showing the eddy covariance station. We also do regulated deficit irrigation on the same plot. So this is a huge piece of land. Here we have the sensors with enough fetch to be able to measure or control, where we put 100% of the ET. And we have treatments where we put 70% of the ET, 50% of D, or 35% of DT. This is the other topic I'm telling you about my PhD, but all the things I'm showing you is here in this area where we're assessing evapotranspiration. Some of the results, basically we are able to measure ET properly by the methodology running through doing the both techniques, doing surface renewal and eddy covariance as a residual. Okay, we're measuring since 2018 all the way to this last season, 2022. I'm showing just the first 2 seasons, and the technique, as you can see in the blue line, it has a pretty good accuracy against eddy covariance. The only difference is the technique tends to overestimate ET a little bit, especially in the first stages of growth. We are trying to fix that from the season 2021 on, adding a new thermocouple that it's not fixed as this one. This is the thermocouple originally we measured on 2018 and 2019. And we add a second thermocouple here, which is mobile, and is has the same height as is associated to the fetch of the station here when it's completely grown. So I'm not showing that result today, but this improvement has a little bit of help on the assessment of ET. What I'm going to show you is the way we are modeling the final KC. We're using 3 different ways to measure it. The first one is based on time, which is the DDF, so days after flowering, so time based, so it's days, and GDA, so growing degree days in green, and also ELP, which is a phenological stage, okay, based on Eco Lawrence. So this is the way that if you see ET on the time moves in this scale, and this is the way that we can model KC on the time using these different scales. We want to be sure, we want to see which scale has the best accuracy over time, and see if we can build a KC curves under ALP or DDF or GDA. Also, we're thinking on how's the resolution on the way you're building the KCs. So if you were using a modeling strategy where we are seeing the KC in terms of daily measurements, and we are trying to figure out where should be the frequency of testing, of getting the data on to be able to have more accurate KC. So it's very simple, like if the ET changes a lot, which it happens a lot at the beginning of the season because your plant is growing, you should have a higher frequency on the measurements, because plants obviously are different day after day, and not as when you have the peak of your growth. That's what we're doing with the different scales. We're using a nonlinear optimization algorithms to be able to discover which is the best frequency to measure and assess ET to have a final KC. And the optimizations, not in all the cases get better results. Today, we are seeing that the best way to build models of KC, it's been in a steady state of 7 days. This also associated with GDA, which is 64 growing degree days, steady state. One of the hypotheses what we have also is might be because of the way we irrigate, because we irrigate every 7 days. So maybe also that impacts the accuracy of this building these curves over time. But this is a result of the validations over the first 2 years of modeling and the 3rd year of using a new data set. And we are using right now this KC curve, that is this one in blue, to exploit it and to see if we can actually give irrigation to plants in a very accurate way. Right now, we built this platform. I didn't tell you at the beginning, but I work in Viña Concha y Toro, and I'm doing my PhD on Citra, so I have to do both things, exploit and do my PhD. So this is the part where I'm working on actually use these KC curves to be able to irrigate. We developed this platform where the grape growers of the company can program their irrigation at the beginning of the season and check them out every week or every other week to be able to determine real demand over the crops. Until now, it's working pretty well. This last season on 2022, we have 1,000 hectares monitored with this system with an 18% savings on water, which is water here for enough to 10,000 people. So that's what I wanted to show you guys. Thanks a lot.
Thank you very much, Sebastían, for your interesting presentation. Okay, our next topic presentation is carbon water coupling mechanism of global agro system and the changing environment. The speaker is a PhD student, Sang-Hu Lu.
Yes.
Okay.
Yes. I'm sharing my screen.
Okay, perfect.
Oh, can you hear me? Can you see the screen?
It's nice. Yes, the screen is.
Yeah, thank you.
You can put in mode presentation.
Okay. Good morning and good evening, everyone. Thanks for offering this chance to discuss my work. My name is Sang-Hu Lu, and Professor Tian supervises my work. Now, I would like to share my research titled The Carbon Water Coupling Mechanism of Global Agricultural System under Changing Environment. The presentation consists of 4 parts, and first of all, I would like to introduce my background. At present, the global population is growing at an annual rate of 100 million, which increases food demand and water consumption rapidly. By 2050, the upper will increase by 70% and the later will increase by 19%. Although the rain-fed agriculture produces 60% of food globally, it's highly dependent on climatic conditions and vulnerable to water and heat stress. Therefore, the irrigation has become an effective method to climate change. Drought is concerning a critical factor that affects the sustainability of agriculture, with about 70% of available water used for irrigation. So above all, improving agricultural water productivity is the key to balance the contradiction between food and water scarcities. Satellite sensors have features such as high resolution, large spatial scale, and long time series. making it possible to characterize the spatial temporal dynamic patterns of AWP and pixel scale, and being widely verified and applied. Historical seasons help us set up better water and land regulation. However, systematic monitoring is still needed, especially in exploring carbon-water coupling mechanism. Above all, the objective of our study is first, quantitatively characterize the temporal and spatial patterns of agricultural water productivity in the global agro-ecosystem. Second, explain the contribution of main driving factors to GPP, ET, and AWP. Third, review the mechanism of irrigation on global AWP under the core effect of climate factors and human activities. Our study area is based on global agro-ecosystem, and we pay attention to irrigated agriculture and rain-fed agriculture. We used evapotranspiration and growth primary remote sensing data from GLASS and MODIS. Simultaneously, we used the multiple land use, land cover data, climate data, and some statistical data. In terms of research method, firstly, we adopted the above formula for the calculation of agricultural water productivity, net solar radiation, and vapor pressure deficit. Secondly, we used the regression model for the goodness of fit test and correlation analysis, and MCAM model for mutation test and trade analysis. Next, EMD model is used to estimate the change trade of variation complex time series, which is decomposed into fixed model function and trace terms through several iterations. Finally, the modeling experiments are used to isolate the contribution of GPP and ET total trade in global AWP, and the experimental design is shown in the chart. Based on the above data and the research methods, we concluded 3 results as shown afterwards. First, the spatial temporal variation of ET, GPP, and AWP in global agro-ecosystem were quantitatively characterized. The data detected significant spatial heterogeneity and has rules in latitude and longitude. AWP had a higher value at mid and high latitudes and a lower value in India, North China, and the Middle East. Over the years, the value range of AWP in various regions was mainly 0 to 4 gram in carbon multiplier water per kilogram. With the spatial distribution of the trade of GPP, ET, and AWP from 1982 to 2015 present here, we could tell that this regional difference shrunk from 1982 to 2000, but the percentage of pixel with the rising trade increased year by year. By 2000, the percentage of pixel with an accumulative growth trade increased by 45%, 84%, and 47% in GPP, ET, and AWP, respectively, and later decreased. The temporal variation further confirmed this finding. We found that the interannual GPP showed an increase in trade first, then decreasing and trending to be stable, reaching the peak in the 2000s, with a variation range of 1428 to 1596 gram in carbon square meter per year. ET showed a significant growth rate with an increase of 1.84 millimeter per year, and the interannual AWP showed an increase first and then decreasing on trade, with a variation range of 1.51 to 1.64 gram in carbon copper multiplied water per kilogram. In the second part, we discussed the driving factors of spatial temporal variation of AWP. First, based on the EMD model, it's judged that AWP appeared inflection point in 1999 and showed a trend of increasing first and then decreasing. Based on the modern experiments, the results show that the change of AWP trend was mainly controlled by GPP and the positive trend of 0.011 gram in carbon multiplied water per kilogram produced by GPP offsets the 0.004 gram in carbon multiplied water per kilogram contributed from AT, which made the overall performance as the increased trend. It can be concluded that the increase of GPP made the AWP improved. As we mentioned, the water, heat, and the crop conditions are commonly accepted as the key factors affecting the change of AWP. Based on the attribution analysis of main driving factors to GPP, ET, and AWP, we found that the water condition was the main driving condition to GPP and AWP, with 53% and 58% of area was controlled respectively. And the heat condition was the main driving condition to evapotranspiration, with 54% of area was controlled. Most preciously, for AWP, the VPD and SMR were the main driving factors, controlling most of farmland in Eastern China, Eastern Europe, and the US. As we mentioned in part 1, we found that 1999 was the mutation year, so we further explored the mechanism difference before and after mutation year. The attribution analysis of main driving factors before mutation year and after mutation year as present. The results show that the main difference was the water condition control of evapotranspiration was significantly increased by 17%, and the heat condition control was significantly decreased by 16%, which further improved the water condition control of AWP, and specifically manifested in the contribution of soil moisture increased by 4.4%. And this was related with the downward trend of soil moisture. Our results showed that soil moisture showed a significant downward trend after 2000, and the correlation with AWP was enhanced, which made AWP showed a downward trend as well. It can be concluded that the significant downward trend of soil moisture made AWP show an inflection point and a downward trend. Concluding two parts above, we want to further explore the mechanism of soil moisture on carbon water coupling using ground-based and UV-based remote sensing imagery. As related experiment has been conducted, we will display it during the next workshop. In the third part, we discussed the effects of irrigation on spatial temporal patterns of AWP. First, we found that water limited the most of farmland, taken proportion of 64% in total. Furthermore, water limitation in AWP was significantly lower than energy limitation, where the annual average difference was 0.27 in carbon multiplied water per kilogram. And this was also exist in the multi-year average monthly AWP. Further, we are going to discuss the difference in driving mechanism. We found that water limited cropland was more sensitive to water condition, and the sensitivity was increased by 9.6%, especially to precipitation, which was increased by 7.7%. And we found that the water limited farmland was mostly arid areas, the irrigation was an effective solution which led the growth of irrigated cropland year by year. Finally, our study demonstrated that the effect of irrigation on AWP. The result revealed that irrigated cropland has the higher AWP than rain-fed cropland, increase of 3.3% to 28.2%, which showed that irrigation was beneficial to increase agricultural water productivity and mitigated the downside influence such as climate change. There are many similarities in climate between China and Chile. So next, we would like to figure out the difference and the similarity between the aerial and semi-aerial plantation structure and the carbon water coupling mechanism. Overall, our study completes the carbon water coupling mechanism of global agricultural system, and the study can be summarized in 3 parts. First, our finding demonstrated that the change of AWP trade was mainly controlled by GPP, and the positive trade produced by GPP offsets the contribution from ET. So the growth trade of GPP made AWP show an overall growth trade. Secondly, the study showed that AWP showed a mutation point in 1999, showing a trend of increasing and then decreasing. The contribution of soil moisture increased by 4.4% after the mutation point, and we found that the soil moisture showed the significant decrease in trade was the main reason for the decrease of AWP. Third, we found our research showed that irrigation facilitated the increase of AWP by 3.3 to 28.2% and mediated the downside influences such as climate change. Furthermore, we would like to explore the mechanism of soil moisture and the plantation structure on carbon water coupling using ground-based and UAV-based remote sensing. Oh, well, that's all of my presentation. Thanks for listening.
Thank you very much. Very nice presentation. And
thank you, Samuel.
Yeah, and your presentation indicated that we have a similar weather condition, and will be great to to analyze China and Chile.
Yes.
Okay, thank you.
Thank you, Professor Samuel. Okay.
Okay, our next presentation is estimation of vine water status using crop water stress index based on leaf energy balance and leaf reference under Mediterranean conditions in the Central Valley of Chile. The speaker is PhD student Karen Guter. Karen, you have your time.
Okay. Can you see my screen?
Yes, it's okay.
Hi, everyone. So today I will present part of the work that I've been carrying out during my PhD studies. And in this case, I'm presenting the work estimation of vine water status using crop water stress index based on leaf energy balance under Mediterranean conditions in the Central Valley of Chile. And this work emerges because of what's been mentioned on other presentations. It's because of the water scarcity that we're facing, mainly in Mediterranean areas, which is because of climate change, among other factors, and the decrease on precipitations, mainly on these Mediterranean areas. So this scenario limits greatly the agricultural production, and in particular, also the grape growing industry. So it is demanded that water is managed in a sustainable way, And in this sense, we have several water management strategies, among which regulated deficit irrigation stands out, because it's a strategy that is able to decrease water use on the phenological stages where the plant is far less sensitive to water stress. But it requires adequate water status monitoring in order to avoid imposing a severe water stress to the plant, generating permanent damage. In this sense, there are several physiological measurements that are used for this, among which plant water potential stands out. And in this case, we have two types of measurements that are widely used, which are midday stem water potential and leaf water potential. And in this case, midday stem water potential is far more precise, and it has the ability to integrate soil, plant, and atmosphere conditions, but has the main disadvantage of being really time consuming. And in the case of leaf water potential, it is more used than midday stem water potential, given that it requires less time for the measurements. But it has the disadvantage of not being able to represent the entire plant, given that it only represents the measured leaf. So, resuming, both of these methods are destructive, time-consuming, especially midday stem water potential, and they are unable to characterize the spatial variability of the field because they require a large number of measurements. So we ask ourselves, is there an alternative to these measurements? And there is, in the form of thermal sensors. This is because, as we know, leaf temperature is directly related to plant water status. And this temperature can be obtained either by infrared thermometers or high-resolution thermal cameras. Given that these devices work based on the fact that all bodies above 0 degrees Kelvin can emit infrared radiation that determines certain characteristics of each object. So what do we do with this temperature? This can be integrated into thermal indices, in particular into the crop water stress index, which has been recognized in literature as a good plant water status estimator, given that it allows to quantify the degree of stress of a crop, considering in its calculation the effect of climatic variables. So in literature, this index has been calculated through three main methodologies, where we have the leaf reference methodology, the empirical method, and the leaf energy balance methodology, which I highlight in here because it incorporates far more information, climatic information. So what I've mentioned before leads us to generate the general objective of this work, which is to estimate midday stem water potential of a vineyard under different irrigation treatments using the energy balance of the leaf to calculate the crop water stress index. And for this, we carried out an experiment during 2 growing seasons over a commercial vineyard in the Maule region, which is in the central zone of Chile, that has a Mediterranean climate. And in this study site, we established 2 irrigation treatments, one with no water stress and the other one with moderate to severe water stress. And these treatments were managed according to a midday stem water potential threshold. So to carry out this, we used field measurements. First, we carried out midday stem water potential measurements that were made through the use of a pressure chamber, which is in the picture above. And the methodology, as I told you before, is very time consuming because it entails the covering of the leaf in plastic wrap and aluminum foil. And we have to let the leaf set for at least an hour before carrying out the measurement. And along with this measurement, we carried out canopy temperature measurements through an infrared thermometer, considering only the middle third of the canopy in order to avoid incorporating non-plant materials such as branches or bare soil. In addition to this, we used climatic variables that were obtained through an automatic weather station in the study site. And we considered variables such as air temperature, wind speed, net radiation, and relative humidity. And now to the calculation of the index. For this, we used firstly the main equation, which is the one above. And to determine the upper and lower limits of temperatures, or T dry and T wet, we used the energy balance method, which, as you can see, incorporates a lot of climatic variables. And this allows us to estimate the value of T wet, which corresponds to the temperature that the canopy would have under well water conditions, and the temperature or T dry, which corresponds to the temperature that the canopy would have under severe water stress. And the novelty of this equation comes in the form of the calculation of the isothermal net radiation, which in this case was calculated through the equation proposed by Ortega-Farias et al. On 2016, which incorporates all the equations that you can see on the screen. In addition to this, we carried out statistical analysis in the form of linear regressions, one-way ANOVA, and we considered two error estimators, which are root mean squared error and mean absolute error. And moving to the results, we first can say that the average climatic conditions for both seasons of study were fairly average, as I mentioned, in terms of air temperature, net radiation, relative humidity, and vapor pressure deficit. And now moving to the correlations, we can see here the correlation between the crop water stress index estimated through the energy balance and midday stem water potential, where we can see a high correlation between both of these variables, obtaining an R squared of 0.68, which is, we could say that it's higher than most of the works reported on literature. And with this equation, we were able to estimate the behavior of midday stem water potential using the energy balance equations. And in this figure, we can see the observed midday stem water potential on the black line and the estimated midday stem water potential using the energy balance. And we can see that the estimation is fairly precise throughout both seasons of study. In addition to this, we wanted to visualize what we saw in the last picture, but separating between the non-stress and the stress treatment, where we can see that the estimation is precise for both cases, but it's far more precise on the water stress treatment. On this table, we can see the error estimators that range between 0.08 and 0.11 megapascals, which is in line with what's been found on literature. And on table 3, we can see the effect of treatments and seasons over the measured variables, where we can identify that there's a significant difference between treatments and between seasons, with no interaction between the aforementioned. And concluding the work, we can say that the crop water stress index is indeed a good tool to estimate water status of the vineyard and has the potential of replacing the traditional methodologies, especially when we consider the inclusion of new technologies, such as the use of UAVs along with high-resolution thermal cameras, which will allow us to precisely characterize the spatial variability of a greater area in comparison to the measurements carried out on this work that, even though are precise, are only able to consider a certain area. Thank you for your attention.
Thank you very much for your presentation, Karen. Okay, our next speaker, the next topic, next presentation is assessment of midday stem water potential in grapes using spectral reflectance indices. Ricardo, Vega, please, you put your presentation.
Perfect. The slide change when I press the button?
Yes, it's okay.
Okay, okay. Well, good evening, everyone in China, and good morning to my colleagues here in Chile. I am Ricardo Vega, PhD student. And in the next 15 minutes, I'm going to present you part of my work titled Assessment of Mid-Diastem Water Potential in Grapevines using Spectral Reflectance Indices. So what's the current context? The grapevine is one of the most important crops both worldwide and in Chile. It is commonly grown in Mediterranean or semi-arid climates prone to water stress where irrigation is required. However, climate change will bring uncertainty in terms of temperatures and precipitations, with a reduction of the latter expected between 25 to 45% by the year 2050. Therefore, strategies to save water and improve quality, such as regulated deficit irrigation, become relevant. And to implement these strategies, it is very important to have a fast and precise way to monitor physiological variables that are preliminary indicators of stress in the plant. In viticulture, one of the most used methodologies to monitor the water status is obtaining the water potential, which involves measuring the pressure of the sap inside the xylem through a pressure chamber. Under irrigation conditions, like here in Chile, it is preferred to use the stem water potential. But as we've seen in the images, it is a tedious and slow methodology because it requires selecting a representative leaf from the middle tier of the canopy, exposed to the sun. Then it has to be wrapped in plastic to limit gas exchange. And next, it has to be covered with aluminum foil to prevent photosynthesis. And finally, wait more than an hour so that the water potential of the leaf equals to of the plant. And after that, the leaf can be cut and measured with a Cholander pump. So it is not a very practical method. So as an alternative, the use of spectroscopy is proposed. But what is a spectroscopy? It's the measurement of the intensity of radiation as a function of wavelength. Let's remember that when radiation hits a surface, a part is absorbed, another is transmitted, and another fraction is reflected. And that reflected radiation has valuable information about the body it hit. Then the matter interacts with this radiation, and if we integrate the visible and near infrared and shortwave infrared regions, it is possible to obtain what is seen in this figure, which is the spectral signature of a surface that is particular for each one, and also it's modified by numerous variables. One of these variables is water that produce peaks of maximum absorption or drops in reflectance in certain bands. Theory indicates that stress lowers photosynthetic efficiency, causing reflectance to increase in the visible region and decrease in the near region. However, various authors, such as the one we see in this figure, have obtained the similar results when evaluating the behavior of the spectral signature under stress conditions. Therefore, it has been suggested that a better way to study this variable is through the spectral reflectance indices, which are based in the combination of reflectance values at different wavelengths, as we see in equations 1 or 2. The advantage of this approach is that they are easy to use and also help to normalize background effects of the target spectrum, reducing noise generated by the atmosphere or the ground. Hundreds of indices has been developed to date. Here in this table, we see a selection of them from the simplest, such as the simple ratio index, or to the more recently developed ones, such as a Webby index, which has been correlated with many variables such as a leaf area index, yield, gas exchange, fluorescence, pigment content, water status of the plant, and carbon isotope discrimination. So the objective or the main goal of this study was to identify the best spectral reflectance indices to estimate the mid-diastem water potential in a drip irrigated vineyard growing under Mediterranean semi-arid conditions. The experiment was conducted during the 2019 to 20 and 2020 to 21 growing seasons from anthesis to harvest in a drip irrigated Cabernet Sauvignon vineyard located in the Pencahue Valley here in the Maule region of Chile, trained on a BSP system with a soil of loamy texture. A randomized block designs what establishes in order to block the effect of a compacted layer present in the soil. The experiment consisted of 2 irrigation treatments with 4 repetitions. Treatment corresponds to 2 irrigation regimes applied from fruit set to verizon with the aim of generate a 2 level of stress in the plants, as we see in this table. Grape by water status was evaluated to the mid-diastem water potential during fruit set to harvest. Measurements were made on 2 healthy leaves per repetition selected of the middle third of the canopy, following the procedure detailed previously. And a model SVC spectrodiometer attached with a leaf clip reflectance probe able to measure between 350 to 2,500 nanometers was used to obtain the spectral reflectance of the leaves. The reflectance was captured at the same time as the water potential measurements, that is at solar noon. All data obtained from the spectrodiometer was processed with Andes, a software especially developed by the authors in MATLAB. This program allowed to smooth and interpolate the spectra with a Savitsky-Golay filter, and then compute more than 300 spectral indices. Then the obtained data was evaluated by means of a linear regression between spectral indices and water potential. Also, an ANOVA was performed for the analysis of the difference between the irrigation treatments. And finally, a linear model based on the best index was constructed with data from the first season and validated with data from the second season. So here are the results. In this graph, we see the behavior of the stem water potential throughout the experiment in the first season. We see clearly that the treatments differ, with X0 having an average of around -1 megapascal, which coincides with the plants without or too light stress. And on the other hand, the X3 treatment maintain a sealant potential values lower than -1.5 megapascals, which correspond to moderate to severe stress, recovering only at the end of the season. Following the Van Leeuwen's criteria, a threshold of -1.1 megapascal for stem water potential was defined, which allow to separate the leaf spectra into 2 categories, not stressed and stressed at the time of field measurements. Here it can be seen that water stress induces a drop in the reflectance around the entire electromagnetic spectrum, which is consistent with what's observed by other authors. The analysis through spectral reflectance indices yielded significant linear correlations between several indices and the stem water potential, which coefficients of determination values reaching up to 0.73%. As can be seen, the indices that deliver the best results are those that make use of bands in the visible region of the spectrum, especially around 500 nanometers, These good results in the visible are probably due to the fact that these bands are associated with photosynthetic pigments, specifically to photoprotective pigments of the xanthophyll cycle, which are one of the main adaptations of plant leaves to environmental adversities. In this image, we graphically see the best correlation found, which is the pre-index, which was used later for the creation of the model. Now it is known that water stress can reduce photosynthesis in 3 ways: by limiting CO2 entry to the leaf, which is an stomatal limitation, also by decreasing CO2 diffusion to the mesophyll, or by inhibiting the photochemical and metabolic processes associated with photosynthesis. The latter is what explains the good correlation obtained in the visible region, because these indices measure changes in photosynthetic activity. In this case, the band around 530 nanometers is associated with the photoprotection processes provided by the xanthophyll cycles, while the bands around 570 nanometers are used as a reference, since they are not affected by stress. And finally, here we see the behavior of the model to predict the stem water potential. Points above the 1-to-1 line correspond to model overestimates, and point below the 1-to-1 line correspond to the model underestimates. As conclusions, we can say that good correlations were obtained between several spectral indices of the visible region and the stem water potential. Work remains to be done to improve these estimates. For example, the spectral signature of the same leaf could be taken during the experiment to verify if the predictive power of the spectral indices degrades over time or not. Also, other approaches could be used to analyze the data, such as multivariate analysis or artificial intelligence. However, these good results in the visible spectrum open up the possibility to develop a low-cost device that make use of these indices and allows irrigation management. Thanks for your time.
Thank you very much for your presentation, Ricardo. Well, we have some time for some questions, discussions, ideas. I think it was a great workshop. Very nice presentation. I think we have a very good students, Faye and Sufen. I'm really happy about that.
Any questions?
Okay.
No questions? Oh, Samuel, so I will share my screen with you, and I need to share something with you, I think.
Yes, perfect. Go ahead.
Have a try.
Yes, I have a suggestion. I think it's a very good idea if you share the emails of all of us to contact later.
Okay.
Yeah.
How look? So can you see my slide?
No, not yet.
Not yet?
No, I see your screen with several presentations, but no slides.
In the file page, maybe you should choose another sharing screen.
Oh.
Oh yes, that's right. You have to change.
You need to stop the sharing, yeah, maybe.
Yeah.
Start new sharing, maybe. about the presentation.
How about this time? Can you see my slide now?
No,
Still not working?
no.
Sorry. So Ricardo, have you already stopped sharing your slide? Ricardo, have you already stopped sharing your slide?
Yes,
Yes.
I stopped sharing.
Yes.
Oh, but why I can't sharing? How about
Yeah,
this
it's
time?
coming now, it's coming.
Ah, it's working. Okay.
Oh, no, you have another screen.
You still not, you
No,
still can't
yes,
share.
yes. Now, yes, okay.
Yeah, okay.
Perfect.
Yeah.
Perfect.
Yeah, I think all of you have done perfect presentation. Yeah, I think some of Chile side, for the PhD students in Chile side, we have some common interest. Yes, you have just found we have done some research in we also have done some research in Shiyang River basin. In our experimental station, we have done some vegetation index monitoring. We have CWRCE monitoring. We have ET monitoring. We have some crop mapping monitoring. Yes, so we have some common interest. So based on our joint program, we have something to do in the next 2 years.
Yes.
Yeah, so based on the joint project as we discussed last time, firstly, the first thing we can visit each other. For example, yeah, the joint summer school for the graduate students. I'm not sure, maybe it may depends on CWRCE effect. Yeah, and also the second is the PhD students exchange. Yeah, based on the above presentations, we can find that the Chinese side and the Chile side have some common research interest. So maybe then from next year, we may have some PhD students exchange, and also about the joint workshops.
Yeah.
As your last email planned, yes, maybe in this September, October, yes.
Mm-hmm.
So the last one is that we may have some joint experimental build some joint experimental station. Yeah, in Shiyang River Basin, Northwest China, and also in Chile, yes. So I think based on this joint project and based on this workshop, it bridge the gap or the distance for the Chile students and Chinese students, and it bridge the joins the graduate student to the top experts. Yeah, it's very a good thing. So for the presentations about our collaboration on our research and studies, as we discussed last time, is how to compare our result both in Chinese side and in the Chile side. Yeah. And the second is, as we discussed last time, so how to calibrate the ATS model in China. As we discussed, yeah, as we discussed last time, I think, for example, it's very easy to run the model, 3 temperature model, to simulate or calculate the evapotranspiration. We just need to prepare some input data, and then we can run the model in 1 or 2 minutes.
Okay.
Yes, but when our 2 students are preparing the data, they have sent an email to Louis and they wonder if they can have the model or the procedure. But maybe Louis is very busy, so maybe he has not read the email yet. But I think if we can get the model or the procedure, then we can finish the joint paper earlier this year, maybe. Yeah, this is what I would like to mention at this time. Yeah.
Perfect.
Okay. About the workshop, we may keep in touch closely and make a decision later. Yeah, with Professor Wang maybe. Yeah. So this is what I would like to mention about this workshop. So I think maybe we have, if the students have time, have some discussions or have some questions, they can ask now. Yeah.
Yeah.
Very perfect presentations.
Yeah. Yeah. Well, if the student, for example, they want to get some connection each other, well, we can share the emails, and you can also discuss later about different topics and ideas. And well, the idea is in the future to get some, of course, some joint publications. This will be great.
Okay.
Also, Faye, we have, as I told you before, we have a special issue in irrigation science for UEV applications, ET estimation and crop water stress estimation using UEV. Maybe we should put a paper together for that special issue.
Yeah, it's really a good idea. Yeah, my question, I want.
Another good news, irrigation sign increased the impact factor. Just we got 3.51 right now. This is a good, so we can do that. And also the workshop for, I think for October, I think, you know, the workshop will be for general, we can invite people, general people from China, from Chile, and we can show a presentation about our publication. You have 2 publications, good publication in UEV, I think. And I have 1 or 2, so we can maybe put those publications in very nice presentation, 4 presentation or 3, and this is, I think, will be the workshop. I don't know what you think about it.
Okay, that's a good idea, I think. So,
okay, so we have a good plan for the future. We have, you know, good ideas, a lot of data. We have to work really hard. Forget the publication, and was for me a great to see you, to know you, to know your students. Yeah, so well, I think I met some. I don't know when I was on China in Beijing. I don't know if I met one of them, but so okay, we can keep in touch. I don't know. You have another question? No more. Algún general question? No. Okay. We close then this very nice workshop, and maybe next year we can plan another workshop with more results. Maybe I think it's a good idea to do that. Okay. Okay. Faye, I don't listen to you.
Yeah, in China, I think the everything is returned to normal right now. So from today, the teachers are allowed to return to the school with no limitations. So I think maybe at the beginning of the next year, we may see Professor Samuel in Beijing, and we can have discussion in CAU or in the experimental station.
Yeah, yeah, will be great. Yeah. Let me take the final picture for. Can you put your cameras please on?
So
okay,
you can open your video.
This is for okay. Thank you very much. Have a nice evening. Good night.
Thank you, Samuel.
Bye bye.
Bye bye. Bye bye. Bye bye.